a Friday morning. We're going to do the second web task associated with real-world performance. You're probably, if you live in Europe, you're probably on vacation and you're listening to a recording of this. And if you're in the Asia-Pacific region, you're probably asleep at this point in time and, again, listening to a recording. So most of the people online are probably in North America. As I say, it's not going to really make too much difference. It's just it means that the interactive part of this will be, we're only getting a third of the audience today, but that's life. So what I'd like to do is introduce the fact that we've had some more videos have been launched over the last few days, and talk about some things that are going on in real-world performance. And just to open it up, if people haven't met me before or haven't sort of come across my team, I'm Vice President of the Real-World Performance team here at Oracle. And I have a very simple way of looking at performance, and explaining it. And the simpler we make it, it usually means that we get the right answers and we also get better performance. At times, it seems that people overcomplicate the whole situation and make things difficult for each other. So, from what I've found over experience, that good performance on today's systems is rarely an accident. People don't fluke excellent performance. It's usually engineered and thought about up front. It's very rarely retrofitted into a system. It actually does need to get thought about and designed and engineered in. Which gets me on to the next phase that I tend to see is that most companies and people tend to get the systems they deserve. I think a lot of us understand what I mean when I say this, and this was taught to me by one of my mentors early in my career when I was getting extremely frustrated when people were making poor decisions at every decision point, basically to try and make their life easier. But as a result, the system performance was getting more and more erratic and more poorer. And, it is the reality of the situation is people get what they deserve in the end. And if they've got poor system performance, the usual reaction is to either blame people or vendors or things like that. But if you actually look historically, you can see that there's been some major whys in the road where people took the wrong decisions and things went wrong. And the last thing is something that is the mantra for my team, the Real World Performance Group, is that we really hate hearing this expression that I hear far too often, that the performance is good enough. Really, in many cases, this is performance set by business metrics, and we call this sometimes business performance by MBA, rather than actually figuring out what the performance of the system is capable of, what the hardware and software is capable of doing. So we always aspire for excellence in getting the best out of the resources, rather than just meeting the business requirements, because we know, and I think everybody on this call knows, that business requirements can change at a drop of a hat. So suddenly good enough today is awful tomorrow. And so we should always be aspiring for the best and aspiring for excellence. And it's usually when a new hire joins my group and they come and tell me, oh, we think performance is good enough, it usually means that they've got a frown on my face and they're going back to work that evening or the weekend to get it to excellence. Because, just meeting the requirements to me is not a sign of good performance. Getting the performance to that we're fully utilized and optimizing the hardware and software is what good performance is about to me. And there is a subtle difference, and I'm still having to teach this every day in every management meeting I go to visit. So that's life. Anyway, let's talk about real-world performance. Really, everything falls under these three categories as far as I can see, is incorrect use of the tools and the products. This comes from, something that we learn intuitively, trying to use a hammer as a screwdriver, and in many cases, but in the database space, it's very often database incorrectly installed, incorrectly patched, which is the first incorrect use of the product, and then just trying to use functionality in a manner it wasn't designed to be used. The second big issue that we're really seeing is the big little data design challenge. They've got little data algorithms trying to run against a large data set, and we'll show you in some of the videos why this can actually be a pathological situation. And then the first one is, the last thing is we see here is a human nature issue. Everyone wants to be the hero. Everyone wants to provide the quick fix, the solution. How many times have people suggested things without even understanding what the problem is? And this just wastes time. May sound fantastic in a meeting when everyone's in a war room and stressed, but unless you understand the problem, the chances of you getting the right solution is highly minimalized. So, these are the fundamental mistakes that I see being made daily in the space of performance. And in fact, when my engineers come to me and tell me about projects, I usually drop the history of the project into one of those three categories, or sometimes two at the same time. And it happens literally every week, every day. So what we're going to talk today about is the new videos that were put online, which is all about leaking and set-based programming. And then we're going to just talk about what makes a great real-world performance engineer. So let's talk about leaking. Leaking has been done by programmers for as long as programming has been going on. People have allocated resources and then through flaws in their programs forgotten to give them back. I'm sure that most of the people online have been C programmers once in their life, and they've made a malloc call and they forgot to free it. And then they re-entered the same piece of code and they allocated more memory and they forgot to give it back. As a result, the program got bigger and bigger and eventually ran out of memory. But if we forget about memory for a little while, what about programs that take out database resources? And I've listed out things like with cursors, sessions, locks, EQ slaves. What happens if we had a program that was allocating all those things and forgetting to give them back, especially when some of these resources are finite and you can't get them back and they're not an infinite supply of them? Although in many cases what we see is people are doing things to basically devalue all the work we've shown in the previous videos we talked about in previous sessions in terms of getting cursors and sessions to be fixed and finite and under control. They're basically, as soon as they're rolling something out in production, because they have a bug in their application that leaks resources, and they have to set these things like processes and open cursors to massive values just to make the application run for a period of time, until such time it actually just blows up. And with that in mind, this is what the videos is about. And it's really why a real-world performance engineer, when he sees an application set with processes set to thousands and open cursors set to one, won't immediately suggest reducing these values, because he or she knows that they need to be a little bit cautious, because if the application hasn't been checked for leakage, their changes will result in the application grinding to a halt in about 30 seconds. And we'll show that in the videos. And so, whilst it's very good of us to explain the computer science of why it's important to have a finite connection count and manage resources effectively, we need to understand why people have over-allocated, and it's usually programming bugs. The problem is that these aren't tested for in the QA process, and we'll talk about that in the video as well. And, probably the majority of the times that we see unstable environments with over-connections is a result of programmer bugs. And so it's a twofold thing. The system architect needs to architect the correct number of connections, but we also need to instruct our programmers as to the bugs that they may create and teach them how to test for them. Having done that, we're in a situation where we may be able to implement the blueprint designs for a scalable, predictable connection strategy in online system. So that's kind of interesting. The next most interesting thing is we're going to talk about set-based programming. And the videos here are really dealing with the issues that we're seeing today associated with programs that have been written, sort of object-oriented programs or row-by-row processing, or some of my colleagues call it slow-by-slow. And they end up eventually having to run row-by-row or object-by-object down a huge list in batch. And this batch process never finishes within acceptable timeframes. And as a result, people are complaining that the database either doesn't scale, or it doesn't perform, or their batch windows are becoming a really big problem. And again, it comes down to the wrong programming paradigm and an object by object or row by row technique being used when we should be addressing the sets of data. Having recoded techniques to be a set-based technique, we often see, up to 1,000-fold speed up. And when things get 1,000 times faster, we're taking things from the hours to the seconds. The challenge is that set-based programming is not done very often. It's not understood by programmers. It's harder. It's more sort of intellectually harder. But there's plenty of tools within SQL to enable you to do set-based techniques. However, in many cases, the programmers never got that far in the manual and never got to learn it because they're learning SQL on the job and they're delivering functional code. They're not delivering fast functional code. In many times, these things get worse and worse by religious issues who determine that all their application logic must be executed on an application server. So they bring one row over the network one at a time and then suddenly find themselves having to go down the list of millions of objects. And really, it gets back to what we learned from schoolboy maths. If each execution takes a short period of time, but you'll multiply the number of iterations you have to run is a very big number, you still end up with a very big number. And so we use these numbers here just to give you an idea of how long it would take to run a batch job serially if each row process took a millisecond, which could be, say, a call and an invocation over the network, round robin. So you can see that if it's a millisecond, we can do 1,000 in a second. We can see very quickly by scaling through the million and billion and eventually trillion objects that we can be leading to 32 years. This is quite a terrifying multiplier because we're now actually seeing companies generating in the order of trillions of rows a day, web-based traffic and clicks. Billions of rows is not unheard of at all. And so, daily events and processing down billions of rows. We need, the only way we're going to get some of these batch jobs and data correction and verification and validation process to run, we will have to use a set-based technique. And set-based programming and using core database parallelism allow you to exploit the hardware such that you can actually get the thing finished. And to a lot of people, this will mean complete rewrites of code. But what we've done in the videos is race existing code against interim solutions and ultimate solutions. And we advise you to have a look at the video, look at the code, and start seeing, have I got constructs like that in my application? And then the last thing we really want to talk about is what would make a really good real-world performance engineer. This last couple of weeks, we've had a couple of headcount open up in my team, and so we've been using sort of social media techniques to see if people would like to become real-world performance engineers. And we've done a lot of internal thinking within my team, what really makes a world-class real-world performance engineer. And reviewing a lot of the resumes that have been sent to us, we recognize that there's this perception of what people think makes a really good performance engineer and what we think makes a really good real-world performance engineer is very different. What we have seen is a lot of resumes of people who are what we would call a platform tuner. They like twiddling with init.aura parameters. They like playing with operating system parameters and stuff like that. But they really haven't learned to understand the problem, and what they're doing is they're just fixing symptoms of things that look wrong in the database. They haven't taken a top-down holistic view of the whole system. They're just basically twiddling within their own space. And this really is most frustrating because the actual performance gains from doing this is so small. And with the advent of the more engineered systems or balanced systems that we're seeing coming out of Oracle today, there really isn't very much twiddling to be done. And if there are twiddling to be done, it may be detuning. I can't emphasize the number of Exadata systems my engineers have been on where they've had to undo the added value that so-called platform tuners have done in terms of damage to the system, or have restricted core database functionality that has restricted performance. And so the real world performance team, we don't really hold and spend much time on platform tuning. We assume the platform is tuned if we pretty much have got most things at defaults and we have a well-balanced piece of hardware and it's well engineered together. If there's massive imbalances in the hardware and you have much more CPU than I/O bandwidth and things like that, that's just a straight capacity planning architectural challenge, and you can't tune your way around that. But what we do tend to see is that a lot of people try to, and this is really a function of not being able to recognize what the problems are and adjust. But there's this sort of belief that, and it's something that I have to deal with at the management level daily, is that there's this belief that we can just fiddle away and make everything go away. And if there isn't enough hardware, and it doesn't matter how much tuning and fiddling, you can't make a difference. We're also dealt with the fact that there's always this restriction of people who don't want to change code, even if the code is awful. And there's also a belief that we can actually tune bad code by fiddling things underneath. And this is just not going to happen. I've been working with a company who had been doing this for quite a period of time, and they squared to me the other day and they said, Andrew, you know, we have been fiddling around with parameters for years and we've never moved the performance needle. The day we started actually investing intellectual capital and changing our application code, we saw the performance gains you spoke about, the game changed, and suddenly we were seeing performance gains on all platforms and all environments, and we've added to our intellectual property within our application stack. And really, this is the key. We have to have a really good real-world performance engineer who basically will be technically adept from the application code almost down to the assembler level at the bottom of the system. And this is where time and experience comes in, because they will have learned the relevant technical skills. In many cases, the resumes I just see this huge log of things that people claim to be experts with, and think that qualifies them. But really, it's not the only thing that qualifies people as world-class performance engineers. Being familiar with the technology and being able to drive it is important, but this is also something that can be learned on the job. But really what we're looking at in terms of a performance engineer is the ability to measure and to extract the data and the proof point to figure out where the time is being spent in a performance problem. Because performance is all about measure of something over a unit of time. So if you can actually extract the data and figure out where the time is being spent, in many cases you have effectively been able to define the problem. We're spending too much time in one operation or one algorithm or one thing, and it should be segmented, you know, at all layers of the application. If we only look at the bottom 10%, we won't get a holistic view of it. And this skill set is really rare to find somebody who can actually look at the whole thing holistically, find out where all the time is being spent, and recognize where things are either algorithmically weak or components are not working as designed, whether there's a bug, there's a defect, whether the application code is wrong, is the skill that we like to see developers in a performance engineer. This is the important bit. Being able to holistically figure out where the inefficiencies are. What I also notice is that basically good performance engineers use their peers, they use their network, their skills, and they're focused on making performance orders of magnitude better. To be honest, to use my team on a performance project that made things 10% better is a waste of time. We can just sit around for 18 months and let Moore's Law figure that one out. What we're looking for is orders of magnitude performance. So if somebody wants to be a world-class performance engineer, their goals should be at least 10x or 100x or 1000x, or in fact, one of my engineers showed me this week, she actually got something 10,000 times faster. And that was actually back to just basic real-world performance, that in fact that the users of the product weren't using the database properly, and she basically returned everything to its default value, gathered the correct default statistics on the schema, and it was 10,000 times faster. And this is, again, something that we see all over and over again, selectively detuning of products, and it just drops into these categories all the time. So it's basically the ability to figure out where the time gets spent and recognizing what's suboptimal. And it very rarely is a case of using the symptoms and trying to fix the symptoms. It's using the symptoms to recognize where perhaps we're algorithmically weak. Now, the challenge, having figured out where things are inefficient or wrong or not working correctly, is that you've done step one. You've identified the problem. Now, the next skill we look for performance engineers, and this is where really a performance engineer becomes a change agent, instigating change to improve performance, because it's not always easy. The performance engineer has to sort of do a certain amount of social engineering. Very often, developers don't like to be told their code doesn't work. In many cases, they may be using a product that has a bug, and basically they have to make sure that they can produce a test case for the bug, and such that the developer can fix the products. And so basically, they're going to be able to use the data that they've gained on the earlier phases to actually produce the evidence that there's a performance issue and promote a solution to it that involves changing code. And within real-world performance, I don't care where the code gets changed, in the application code or in the RDBMS in itself. My team logged a lot of bugs to improve the efficiency of the database. But in all cases, whether we want to initiate change in the application or whether we want to initiate changes in the database itself, the performance engineer has to produce the data to win the argument to initiate the change. It's not something you can throw over the wall and just hope someone's going to fix it. You need to get integrated, propose the changes, get buy-in from the changes, produce the evidence of the changes, maybe produce prototypes and show the differences, and basically get people on board. And you may find that actually the same mistake is being made by hundreds of developers all over the same organization. So having won the argument once, it's time to socialize that issue over and over again, such that other developers within the organization don't make the mistake again. And the final thing that really shows a sign of class of a performance engineer is that they see them through into production and see the benefits of their work. So really, this is really the sign of a successful performance engineer. They've got the changes they wanted to get into production, and they're seeing the benefits of it. And in many cases, a really good engineer can make this happen in a matter of hours, minutes, days. Sometimes it takes years to see this rework, because there's a lot of corporate bureaucracy and resistance to change and risk aversion and things like that. But in many cases, performance is preventing the business from functioning. And so a performance engineer who is savvy with the business and the technical issues and can socialize well can get these changes pushed through to benefit the business. And this is really what we look for in a performance engineer. Somebody who knows how to fiddle with a million init.aura parameters because they read them on Google and they thought all these underscores was the solution, is not what we're looking for. We're looking for engineers who can initiate change and make things orders of magnitude in performance faster and get them into production. And that should always be everyone who claims to be a performance engineer's objectives. So, that's what we're looking for. We are taking resumes at the moment and quite enjoying getting some of them. And we have a few places open. And if this is the sort of style of work you want to do, you'll notice that it's hard work. Performance is always hard work, but if we look at any other engineering challenge where we've had to make things go an order of magnitude faster, like airplanes, cars, and bridges, ships, and things like that, it's taken a lot of hard work to actually get things to go an order of magnitude faster. And this is why it's an interesting, and that's why my team has been around for a long time, and many of my team have actually been doing database performance for over 25 years. Because it's a continual challenge. And at that point, that's about as much as I want to talk about today. I think we have about 5 or 6 minutes, and so I'm open to take some questions via the chat. And Thank you very much for everybody.